Thank you, and thank you for inviting me to give a talk in this very nice conference. So I will present work in collaboration with Mireille Bousquet-Mélou and Baptiste Louf, who's here, and who will talk about something else later in the week. This work is about maps decorated by the Ising model. So I will define these two things before getting further. So the Ising model can be defined on any graph. So you take some spin configuration on the vertices of your graph. So here it's usual to denote them by plus and minuses. This configuration will have a certain probability given by this weight that's exponential minus of beta h, where h is this function here that depends on the alignments of neighboring spins and some external magnetic field B, where B is some constant, and beta is another parameter here that is the inverse temperature in statistical mechanics terms. So, and as usual, we normalize this with the partition function to get a probability distribution that sums to 1. So this is the Ising model on a fixed given graph, for instance, a subset of the grid, and we want to define it on maps. So I'm sure that many people here know what maps are, but just to define things once again. A map is a finite connected graph embedded into a surface. So here, for instance, you have an embedding into the one torus, and it's up to isomorphism. So this means that additionally to the graph structure, you have the information of the cyclic ordering of the edges around the vertices. So for instance, these two maps are different embeddings of the same graph into the torus, but they're not the same map, because you see that here the cyclic ordering of these edges is not the same in the two maps. So in all this talk, I'm going to consider labeled maps, which means that you have an integer label on each of the edges. So I'm not going to write them down each time, but it's the objects that we're going to look at and enumerate. And an important thing is that it kills non-trivial automorphisms to add these labels to our maps. Another important subcategory of maps that we'll look at are cubic maps, where all vertices have degree 3. So here you have an example of a cubic map on the torus. And another important player is going to be bipartite maps. So as the name indicates, you have a bipartition of a set of vertices into black and white ones, such that black ones are only adjacent to white ones and vice versa. So now that we know what maps are, we can define the Ising model on maps in a very similar way as before. We put some spins on the vertices of our map, and to make things easier to draw, we consider these spins to be black and white instead of plus and minus. And we consider this generating function, which is an exponential generating function, just as you saw in Sophia's lecture before. So this generating function, which is for now just a formal object, where we enumerate these Ising-decorated cubic maps with respect to their number of edges with a variable t, their genus with a variable s, and the number of white-white and black-black edges in the spin configuration with respect to the variables new white and new black. And so this is slightly different from the convention that I just showed you before for fixed graphs. But if you take for new black and new white to be these quantities in terms of beta and b, you recover the usual conventions. And as before, we can interpret this as a probability distribution on maps decorated by a spin configuration by taking just the what did I want to say? Yeah, by just taking this weight that's associated to this configuration. If we, for instance, fix the genus and the size of our map, so that we just consider a coefficient in new black and new white, and keep and look at some. Well, extract the coefficient in T and S to keep the size and the genus fixed, and then see what's the probability of having a given map with a given spin configuration. So what's important to understand here is that we pick, well, even though my talk is not really going to be about probability, when we say that we pick a random Ising-decorated map, we really pick both the map, the underlying map, and the spin configuration at the same time, so they're coupled in some sense. So, but for the rest of this talk, I'm really going to focus on the generating function itself and not the probabilistic interpretation that we can make of it, even though I will make some remarks about it later on. So I hope that the definition of this central object in this talk is clear. If so, let me state, oh yeah, just before stating our results, if you want to have some high-level motivation of why we want to look at, in general, statistical mechanics models on random maps instead of fixed graphs like Z to the D, for instance, the fact that the underlying graph is random itself and that it's coupled with the statistical mechanics model that we put on top of it makes it sort of toy model for 2D quantum gravity. And so the asymptotic behaviors of these models can be related or expected to be related to Liouville CFT and very fancy things. But along the way, we also have very nice mathematical structures without going to this very high-level goal. So something else I wanted to say before going to our results is to kind of put this into context about different things that have been done on random maps, decorated or not. So as you can guess, it's easier to work on maps picked uniformly at random instead of being coupled with a statistical mechanics model. And for this, a lot of things have been done. So each time, the people that I'm citing are kind of the first ones that have worked on the associated topic. It's not an exhaustive list at all. So for maps picked uniformly at random, you have, first of all, very famous works by Tutt for the enumeration of maps of genus 0. And for maps of fixed but non-zero genus, you have lots of results from topological recursion. And if you want to look at asymptotic behaviors in a more probabilistic flavor, you have two types of limits that you can look at that I'm not going to define. One is a local limit that relies very heavily on the enumeration results that are just above. And the other is scaling limits, which relies not only on these, but also on bijective proofs of these enumeration results. So here you have results for genus 0, and for scaling limits you also have results in non-zero but fixed genus with recent work by Bettinelli and Vernon. And if you look at high genus, so when you take a map of size n with its genus growing as a function of n, you have enumeration results that come from KP equations that I'm going to mention again later on. And these enumeration results in high genus were one of the ingredients in a work by Thomas Budzinski and Baptiste Louf, where they also get local limit results for this high genus regime. And so if we go now to Ising-decorated maps, what's been done so far is on either genus 0 or fixed genus, so you have kind of an equivalent of the first category in what I said about uniform maps. So you have enumeration results by Tott-like equations and topological recursion. And for genus 0, you also have local limit results with similar techniques as in the uniform map case. So basically, the work that I'm presenting today is kind of filling in the high genus regime, well, not completely filling it in, but starting up the study of the high genus regime in a model of non-uniform maps. So what did we prove? We have this kind of scary statement, but let me go through it with you. So the generating function that I defined earlier satisfies this partial differential equation. So you see that the variable s that enumerates the genus is kind of not very present here. It's just here in this first coefficient, and also in this polynomial that appears in the right-hand side. And apart from this, you see that it's fourth order PDE that is not linear because you have a second term of degree 2 here. And another interesting feature is that even though our generating function is symmetric in u black and u white, this equation is not. And it doesn't seem to be easy to find a symmetric equation. But yeah, and the exact definition of the different terms is not super important, but there are some properties that I will use later on. So before getting to some aspects of the proof of this result, let me mention two important consequences. So the first is that this PDE allows us to compute recursively the coefficients of this generating function. More precisely, if we assume that we have a generating, and it characterizes it. So if we assume that we have a series in T, nu black, nu white, S, that is, so that satisfies two conditions. So the first is that if you look at the combined degree in nu black and nu white, it should be smaller than the degree in T, which, like for I, it's clear because the number of black and white edges must be smaller than or equal to the total number of edges. And also we assume a weak form of symmetry, which is that the maximal, so in the coefficient of Tn, the coefficient in nu white 0 is the same as the coefficient in nu black 0. So it's a weak form of symmetry because we do not assume that the whole series is symmetric in nu black and nu white. And with these two assumptions, we have a recursive algorithm to compute all the coefficients of J, which implies that it's equal to our generating function I because it satisfies the PDE and these two assumptions. So I will get back to the details of this algorithm in the end if I'm not too slow right now. And an important thing to state is that this algorithm is polynomial in the size and genus of our maps. And so I mentioned before that with Tut-like equations or topological recursion, you also get like computations, a way to compute the coefficients of this generating series, but they're exponential in the genus, so it's in practice you have to stop very, very quickly, while our algorithm is polynomial, so it's much more efficient. And we have similar results for non-decorated maps, but that are simpler in the sense that instead of having a recursive algorithm, there is an explicit recursion formula. For instance, for triangulations, you have the famous Golden and Jackson formula. So yeah, this is one important corollary of our PDE. And the second one is that you have this inequality on the coefficients. So if you take the parameters nu black, nu white to be positive, you have this type of inequality for the coefficients in in N and G. And the exact shape is not super important, but we're happy to get this because similar bounds were very useful in the non-decorated maps case to identify, characterize the topology of local limits of maps in high genus. So it doesn't mean that it's the only ingredient that's necessary to get local limits for our Ising-decorated maps, but it's an important ingredient that we're happy to already have. So if there are no questions, oh, I shouldn't take the cable. So let me now get to a few elements of the proof of how we got to this PDE. So the first step is is something that is present in actually all works that deal with Ising-decorated maps, which is a correspondence between Ising-decorated maps and bipartite maps. And so in the case of cubic maps, you get a correspondence with bipartite maps with vertex degree 2 or 3 in the quite natural way that starting from such a bipartite map, if you just forget about the vertices of degree 2, you will have a configuration, a cubic map with black and white vertices, but is not necessarily bipartite. And these colors can be interpreted as spin configurations on your cubic map. And if you try to go the other way, it's obviously a many-to-one correspondence because you can add arbitrarily long chains of vertices of degree 2 along any edge in your cubic map. But in terms of generating functions, it is a very nice change of variables. So I'm not going to dwell on its exact shape, but the important thing is that since we have this nice change of variables, if we prove that the generating function of bipartite maps with these vertex degree constraints satisfies the PDE, then we can apply a change of variables, and this will give us our PDE on I. So now that we're in the world of bipartite maps, a very important feature about them is that they satisfy. So if we now allow vertices of degree 1, we'll have a generating function H that satisfies the so-called KP hierarchy of differential equations, in particular the first one. And so here, so you see that it's very important to allow for vertices of degree 1 because you have derivatives with respect to the variable that enumerates these vertices of degree 1. So we're almost there, but we need to find a way to convert this into an equation on B that doesn't have any vertices of degree 1. So the way we do this is through the framework of combinatorial species that I'm not going to attempt to define in the time I have left. But the idea is that you can write B, so the generating function where we only have vertices of degree 2 and 3, as a specialization of H, where we sent P1 and Q1, so the variables that enumerate vertices, black and white vertices of degree 1, to 0. So we can write this a bit formally as B being equal to this operator theta that sends P1 and Q1 to 0 applied to H. And so what we want to do is write the other terms in this KP equation as also theta applied to something, so that, let me start my sentence again. We want to write theta applied to these derivatives as things that depend on B. And the general philosophy of this is that these differential operators applied to generating functions can be interpreted as combinatorial operations. And so in this way, you can write them down as other generating functions. And then kind of going back again, we can interpret these generating functions of our new objects as differential operators, but this time on B and not on H. So let me just illustrate this claim with the first term. So here we take, we derive twice with respect to P1 that enumerates white vertices of degree 1. And then we apply theta, so we specialize P1 and Q1 to 0. So this means that this generating function enumerates maps that are bipartite with degrees 1, 2, and 3, and that only have 2 vertices of degree 1, because deriving differentiating once with respect to some variable means that you decrease the power of the associated variable. So if you want to have something non-zero when you specialize P1 and Q1 to 0 after differentiating twice with respect to P1, it means that you had no positive power of Q1 and just P1 squared in your generating function. So in other words, you exactly had 2 white vertices of degree 1 and 0 white vertices, black vertices of degree 1. So now that we know what type of maps is enumerated by this, we have to write it again more analytically in terms of generating function B that we like. And so having a map that has exactly 2 vertices of degree 1 that are white means that we have something where so we have these 2 vertices of degree 1 that are necessarily attached to the rest of the map by some chains of vertices of degree 2 that are in. So we don't know necessarily the length of these chains. And you see that in this operator L, you precisely have something that seems to count chains of vertices of degree 2, which is the first, the first term with this, since in the denominator you have 1 minus Z2 P2 Q2, you see that it's the sum of, it corresponds to the sum of the generating function of chains like this with arbitrary lengths. So I don't want to go much more into details, but you see that theta applied to H11 is precisely L applied twice to B plus some boundary term, which corresponds to just having one chain with endpoints being white. And if you do it for all the other terms, you get something like this. And so with this in mind, from this KP equation satisfied by H, you have a PD that's also satisfied by B, and you see that it's starting to get a bit more ugly as we convert things. Yeah, you just follow this dictionary for your theta applied to H something, and you get this. And then you apply the change of variables that we had before to go from a PD satisfied by B to a PD satisfied by I, which is going to be this one. Okay, so I went a bit more quickly than I expected. So it means that I have time to tell you a bit more about this recursive computation of the coefficients of our generating function I. So yeah, so I'm going to write the PD satisfied by I in a slightly more compact way. So just, well, you have this operator omega applied to I, which is equal to, well, what we have on the right-hand side applied to I. And so we want to show that this characterizes I with the assumptions that I said before. And so we start from an arbitrary solution of this problem, of this equation, sorry. And we write it as polynomials, well, monomials in T times polynomials that do not depend on T in the following way. And I'm not going to detail why, but from the definition of omega, you see that if you apply it to one of these monomials, you will get something that is of degree n plus 2 in T, and that the rest is once again something that doesn't depend on t and can be written as the action of some linear differential operator omega n. And if you look at the coefficient of Tn plus 2 in this equation, on the right-hand side, you'll have something that a priori depends on all the polynomials jk, but from the exact definition of the different terms in the right-hand side, it turns out that it only depends on terms up to n minus 3. So you start to see that there's a sort of recursive thing that we might hope to have, because if we, in some sense, can invert omega n, this differential operator, then we'll have jn as a function of terms just up to n minus 3. And the minus 3 here makes sense because n counts the edges of our cubic maps, and so since they're cubic, it's always powers of 3. So it's not that we're missing intermediate coefficients, but so we can recursively compute these coefficients jn if we know how to invert omega n. And it turns out that we can. So with the assumptions that I already mentioned before, so if we assume that we have some polynomial in nu black and nu white with coefficients that are polynomials in S themselves that have degree at most n if you sum up the powers in nu black and nu white, and you assume this initial, this kind of boundary symmetry, then if omega n applied to p is equal to some other polynomial, which will be the right-hand side, the coefficient in t to be n plus 2 in our right-hand side here, then we prove that p can be recursively determined. So the first step tells us, so the idea is that we look at this equation omega n of p is equal to s, and we look at the different, what it means for, well, let me write it. So these are equalities between polynomials in nu black and nu white, and so we just look at powers at the coefficients of these polynomials, and for well-chosen values of I and j, we get something nice. So in particular, if we pick I equals 0 and j equals n plus 2, it turns out that it gives us a very straightforward formula for the coefficient of degree n in nu black and 0 in nu white. And with our symmetry assumption, this is also equal to p0n. And then if we look at the coefficient in so nu black I plus 1 nu white j, we get this. Or in other words, the coefficient in front of pij in this equation is non-zero. And another important thing is that all the other coefficients of p that appear here are for larger values of the first coordinate. So you have pi plus 1, etc., pi plus 2, etc., pi plus 3, etc. So we can now do from the maximal coefficient, so p I equals n, j equals 0, that we know from the first equation, we can now do a sort of right to left recurrence and determine all coefficients of P. And so getting back to our arbitrary solution J of the PD what we got, we see that we determine it recursively. So this means that this equation characterizes I in this set of possible solutions, and that it also determines its coefficients recursively. So now I'm going to try and do something a bit ambitious, which is to show you two implementations of this algorithm in Maple and Sage. So okay, let me start with Maple. So here I want to, in particular, compare the efficiency of Maple and Sage, so which is why I'm keeping an eye on the CPU usage. So, okay, so I just, I don't know if it's readable. Is it better now? Yeah. So I just start by defining what I call the right-hand side in my PDE. So remember that we had this differential operator lambda, and this term q, and then the right-hand side is this function of lambda and q. And this is the part where I write down the recursion. So I have a few things to simplify, like I know that n must be a multiple of 3, and the difference between I, j, and j must also be a multiple of 3. And then this kind of scary part here is just the formula that I wrote down in my slides. And then I just sum these up. Okay, so now I've defined my recursion tool, and if I want to go to like 45 edges, say, I just do this, and okay, this is very quick. It's a few seconds, and I don't know if you. So one thing I want to keep track of is how many CPUs it's using as it's doing the computation. Okay, this was very quick, so it's not super obvious to see what happens. But if we go now to a slightly larger example, it will take a bit more time, and you see that it's starting to use more than one full CPU to do its computations. So it means that there's probably some good parallelizing happening here. And okay, Maple is very nice, but it's also nice to try and use open source software, which is why we also implemented it in Sage. And okay, so is this? Sorry, doing things live is always less streamlined. Okay, so in Sage, instead of doing computations with symbolic variables, we work on polynomials because on a ring of polynomials because it's like more efficient. But sorry, we essentially do the same thing. So we define our, we implement our recursion formula. And now we want to try it out. And okay, so remember that it took like 3 seconds in Maple for n equals 45. And here, if I do the same, you see that it's taking more time. And also that the CPU usage for, so this first line is Sage, well, just gets slightly above one's full CPU, but it's not parallelizing as much, which is like the, I think, one of the big hurdles that make it much slower than in Maple. So yeah, I already had a few helpful suggestions from Mark, who's here, to maybe try and call some functions from Flint, which is more efficient than Sage to work with big multivariate polynomials. But if you have other suggestions to make the Sage version more efficient, I'd be happy to hear them. And of course, we can have a more efficient algorithm at the more theoretical level. We kind of just did a few simplifications that were obvious, but there are probably more efficient ways to store all these differential operators applied to these big multivariate polynomials. But yeah, I'm happy that this kind of live computation part worked. And so to conclude, as I've just said, in our perspectives, we would like to improve the implementation that we have for these recursive computations. The nice inequalities that we have for the coefficients of this generating function opens up some possible probabilistic study of the high genus regime of Ising-decorated cubic maps. Even though a lot of other ingredients are necessary, it would be interesting to go further in this direction. So if we want to exploit further the link between Ising-decorated maps and bipartite maps, these are also known to satisfy the Toda lattice hierarchy, and this would give us other equations for Ising-decorated cubic maps, which would a priori not be partial differential equations, but something a bit more complicated. So part of the work here would be to try and obtain new proper partial differential equations from the ones given by the Toda hierarchy. And we also have reason to believe that if we are specifically at the critical point, the combinatorial structure is much richer than if we take general mu black, mu white. So we would also like to study further this critical point. So I'm going to stop here. Thank you for your attention.
So, thank you for the talk. Are there any questions or comments?
Yeah, thank you for the talk. So I was wondering, the equations that you showed where you get rid of the leaves, as you said. So are there the standard sort of Tut equations for bipartite maps that you use?
I'm not sure what you...
Like the Virasoro constraints for bipartite maps?
Did we use them?
Yes.
No, it's just, well, maybe it's related to this, but it was kind of straightforward with this kind of,
Okay.
you think of what maps are enumerated by
so
this.
you did it combinatorially?
Yeah.
Yeah, okay, thank you.
In fact, I didn't get your comment that the model is symmetric, but that you couldn't get a symmetric equation. So what's the obstruction?
Well, here you have partial differential equation, partial derivatives with respect to nu black and nu white. And, okay, maybe what I said was not super clear. So basically, yeah, if you sum this and the symmetric, you'll have something symmetric. But we would like to have something for the symmetric case. Well, basically, there is no way to get from this an equation with derivatives with respect to nu black. Sorry, if you just want to count the total number of monochromatic edges, which is the symmetric version, where equivalently you forget about the external magnetic field, then you would want to derive with respect to this symmetric variable nu that enumerates this total number of symmetric monochromatic edges, and there is no obvious way to get it from this.
Okay.
Other question or comments? So if not, let's thank the speaker again.